In this video, we'll begin our discussion of thermodynamics and thermochemistry by looking at some of the language conventions in chemistry and thermodynamics. We'll talk about energy, the first law of thermodynamics, work and heat, and what we mean by a state function. So a little bit of background for this section. Thermochemistry is going to be the study of energy in a chemical system. This is one of the big categories for which chemists get paid. Energy consumption is a pretty big deal. We can see how the type of energy consumption has changed as time goes on, but also just the total amount of joules used per year in terms of the energy demand in just the recent decades. So finding more efficient and sustainable ways to obtain energy is a major focus of the chemical industry. Some examples that we have of renewable sources are things like solar. This is actually a still fermenting corn for biofuels. And then, of course, we have good old classic fossil fuels like this nice large offshore oil platform, which is still in our interest to find ways that if we're going to use it in a sustainable and reasonable fashion. So when we're talking about thermodynamics, we're going to define a few things fairly precisely, and it'll be important to understand them when we're talking about the equations related to these problems. So the first thing we'll talk about is the system. The system is going to be the thing we are interested in studying. Usually this is going to be a reaction, and it will be everything that's written in the reaction. So if we have something like this, the system would be the whole container containing the hydrogen, oxygen, and the water that's being produced. The surroundings is literally everything else. Usually in a problem, we'll consider the beaker that's containing the reaction, the room maybe that the reaction is in, but strictly speaking, the surroundings include everything in the whole entire universe besides what's our system. Often we approximate this by measuring something smaller, but strictly speaking, it is literally everything else. The internal energy is the amount of energy contained in just a system. Energy has a few different types, but we'll focus first of all on what it is, and it's the capacity to do work. The units for energy, I'll remember, are joules. This is a compound unit, so a joule is equal to a kilogram meters squared per second squared. And we can see here that work is going to be a force applied over distance. So force, this is in newtons, is kilogram meters per second squared. And then if we're multiplying that by a distance, we get our unit for joules. So work and energy have the same units. One of the most important things when we're talking about energy is this law of conservation of energy, and this is that energy can neither be created nor can it be destroyed. Another way to write this with equations is that the delta E, so the change in energy of the whole entire universe, is equal to 0. So we can't gain or lose energy, the energy is going to be constant. However, what we can do is change it from one form to another, which we'll talk about in a second. And we can transfer from one object or one system to another. So the energy of the universe is going to be the energy of our system plus the energy of the surroundings. And so if the energy of the system goes down, since the energy of the universe has to stay the same, that means the energy of the surroundings has to go up, and vice versa. When we're talking about changing the energy from one form to another, we'll use a different set of terms to define energy depending on what we're talking about. So one of the things we'll talk about for total energy is going to be the sum of kinetic and potential energy. So often, we just have energy is equal to the potential energy plus the kinetic energy. Potential energy is the potential to be doing work or energy that's associated with a matter's position or composition. So you're probably used to hearing this as the potential energy due to gravity. So if we have something really high at the edge of the cliff, it has some energy, so it can have a force over a distance if we push it off that cliff, and this potential energy is related to its distance of the cliff due to the force of gravity. We can also have electrostatic potential energy, so if we have a positive charge that we've separated from a minus charge, we know that positive charge wants to get there. This energy due to electrostatic force is still a type of potential energy. The kinetic energy is associated with the motion of the matter, so as this moves, it would have some kinetic energy due to its movement from gravity. If we release this particle, it would have some kinetic energy due to its motion and its mass. Remember, when we were talking about ideal gases, we could say the kinetic energy on average for an ideal gas from kinetic molecular theory is equal to 3/2 the gas constant times the temperature. And again, this just comes from the motion of particles, in this case, random motion with heat. And when we're talking about the change in types of energy, so while energy total has to remain constant, it can change forms. We can think about the potential energy in this monster drink being transferred to energy, kinetic energy, in the form of maybe doing some awesome kickflips. We also use a few other different terms attached to energy that aren't necessarily kinetic or potential, but just other ways to define the type of energy we're talking about. So electrical energy, for example, is the energy associated with the flow of electrical charge. So this has to do with the electrostatic force, and so this can come again from a charged particle moving. So if we have an electron moving, we can have some electrical energy that way. Or we can have electrical potential energy if we have two charges that want to move but are prevented one way or another. Thermal energy is energy associated with random motions of atoms and molecules. So this is a type of kinetic energy, again associated with random motion. And chemical energy is another form of potential energy that we'll talk about. We know that bonds are driven sort of by a type of electrostatic force. So these are kind of related, but instead this comes from potential energy that's stored in the bonds of a compound, because maybe we can take that compound and then turn it into another compound with a different amount of potential energy, thereby releasing kinetic energy. So let's talk about an example of this. Let's talk about the combustion of methane. So an example of converting potential energy in the form of chemical potential energy to heat energy. So methane, it has this potential energy due to its composition. When we burn methane, so if we take methane and we add it to oxygen in the air, we can get carbon dioxide, some water, and then we also get heat, a fire from that reaction. Remember, heat is related to thermal energy, so we'll get random motion of particles by breaking these bonds, and we can see how this happens. So remember when we were talking about bonding, we know that forming a bond happens because it's favorable, it's going to release energy, and we can have a sort of reaction progress diagram here where we have the potential energy of the whole system, in this case our methane and our oxygen to begin with, and we can see how the potential energy of that system changes as we run a reaction. So to begin with, if we want to break up methane and make something else, we have to break all the bonds in methane and oxygen, and we know that breaking bonds takes some energy. So if we add energy to break the bonds, we could draw up on this potential energy diagram, and we see we have our individual carbons, our 4 hydrogens, and our 4 oxygens. However, we can form new bonds, and remember, forming bonds should be releasing energy. And depending on the bonds that we form, if these are stronger bonds, then they'll release more energy while we're forming them. And so overall, we'll have a net loss in potential energy. And since energy overall can't be created or destroyed, this potential energy that is lost from the system has to be released as heat. So the energy, again, of the system decreases, so that has to go somewhere. And that, in this case, will be to the surroundings as heat. And if heat is released to the surroundings, we call this an exothermic reaction. We'll revisit these terms in a little bit. So the first law of thermodynamics is related to the law of conservation of energy, but in terms of transferring energy. And this is going to say that energy can be transferred between systems and surroundings in the form of either work, so this will be moving something against a force, and or heat, which would just be random motion of particles. This can be written as an equation. So here's our equation for the first law, that the change in energy of a system is going to be equal to work plus heat. And again, in this case, the delta E, this is the internal energy for the system. Let's talk a bit about these two terms. So we'll start with heat. So heat is going to be energy transferred due to a temperature difference. Something that's important to notice here, that the heat, if we're being precise, is actually the energy transferred. So it's not a single value, it always is a change. In this case, it's going to be changed due to a temperature difference. So if we want to think about two pieces of metal at two different temperatures, and we touch them next to each other, one of the things we can ask is which way does the heat flow? Which is a way to say, how is the energy being transferred? So if we think about this, we can have some hot particles here on the metal side. So these are moving relatively fast with their random motion. And we put them next to the colder particles, which aren't moving as fast. And we can think when this heat is transferred, one of the ways that this might happen is this particle hitting one of the slower particles, and then we get a collision. This transfers some of its energy, so it slows down a little bit, and now this one's moving a little faster. And so we can see that the energy exchange is going from the hot side with more energy to the cold side with less energy. So what this means is when I was a young lad and I'd leave the door open at our house in Alaska, and my mom would yell at me saying that I'm letting the cold air in, she was actually wrong. You don't let cold in, you're letting the heat out. So the energy flows from hot to cold. Don't tell my mom I told her she was wrong. Okay, so let's talk a little bit about work. So work, again, is going to be energy required to move an object against an opposing force. So the one we're most used to thinking about would be against maybe the force due to gravity, but we know we do work when we're, for example, driving on a flat surface. That's against the force of friction. We can also do work against forces from pressure and so on and so forth. But this is specifically going to move an object for us against some other force in a specific direction. So one example, we can think about lifting an object against the force of gravity. So that's doing some work. We're raising this up, increasing its potential energy because we're moving it against this gravitational force that's trying to pull it down. If we move a piston in an engine, so something like this, there's a few forces we're working against here. So there's some force due to gravity that's just trying to pull this down. But if these are moving, this car, this is also fighting against the force of friction. And if there's some pressure here, that's also trying to push the piston in the opposite direction. This is moving against the force from pressure as well. So work can be against several combined forces, but the main point is that it has a specific direction and isn't just random motion like heat transfer. Something that'll become really important and actually might differ depending on the discipline that you're in are the sign conventions. So these sign conventions that we're going to talk about are going to be specific to chemistry. You might see them differently depending on how your discipline is defining systems and signs. So for us, we're going to always use the perspective of the system. So when we're talking about heat, if heat is exiting the system, we're going to call this exothermic. And we're going to give it a negative sign. So we'll have a negative Q. If heat is going into a system, so if we have some energy coming in, that means the system is going to get some more random motion in it. And this incoming heat will then have a positive Q because we're increasing the energy of the system. For work, if the system is doing work on the surroundings, so we have our system here, but it's doing some work against the surroundings, that means it's having to put energy against the surroundings, and so it's losing energy. So if it's doing work on the surroundings, we'll have a negative sign for work. When the surroundings are doing work on the system, that means we're adding energy to the system, and so that would be a positive sign for work. So let's do a little bit of practice with this, predicting these signs. So first, let's predict the sign of heat for this reaction. When you're doing this, again, think about how we're talking about the combustion of methane and the idea of breaking and reforming bonds. So for this one, we get that the reaction is endothermic, or Q is positive. And another way to say that, if we're going to write this into the equation, is that heat would have to go on the left side of the reaction. We need to put heat in to make this reaction happen. How would we figure this out? Well, we can look at what's going on in this process. We can see that the products here look like the reactant, but we've broken this bond. So we've broken one bond and reformed none. So if we were to look at that reaction progress diagram, we start at some state, we have to break a bond, and then that's it, we're done. So the energy has to be increasing. That means we're putting energy into the system, and then this has to be endothermic with a positive heat. Okay, let's do some predicting on the sign of work. So now we have a system, which is this gas. So it's just the gas inside. So the surroundings include the piston that can move and everything else. And if we take this cylinder and push it down into the gas, what do we think the sign of work is? When you're thinking about this, we can think about what forces might be involved here. So this works even if this is sideways. So even if we ignore gravity, we can also consider that we do have some forces involved here, namely the pressure from the gas and the pressure from the atmosphere plus the force that we're applying to the piston. Yeah, so in this case, the sign of work would be positive. If we think about this, we have our gas inside the cylinder. The surroundings, in this case the piston and everything else, are going to be compressing the gas. So that's fighting against the pressure, squeezing them in. That would be adding energy to the system. If we're adding energy from the system, that means the internal energy is going up. And so that implies that the work is going to be positive. And generally speaking, if our system is a gas, our work is going to be positive whenever we compress that gas. We can think about the opposite. So if we do an expansion, what's the sign of work? And it makes sense that if we're doing the opposite process, that the sign of work will change. If the gas is expanding, the gas is now using its pressure to do work against the pressure of the surroundings and the piston. So the system is doing work in order to expand, and so the system will be losing energy, and so the work should be negative for an expansion. So let's look at another example with one of these systems with a movable piston. So we now again have our gas in a cylinder. But now in this case, this will be a sample of methane gas, and we're going to raise its temperature. So it's going from 25 degrees Celsius to 75 degrees Celsius and under a constant pressure. So remember, we have a movable piston here when you're thinking about the sign in this case. So we are adding heat to the system. That means the system's gaining energy. This one's pretty straightforward. Q is greater than 0. Now, if we think about work in the system where we're heating the gas, we have this movable piston, but it's constant pressure. The sample expands. So again, going back to our other examples, the system is going to be doing work on the surroundings. So the system should be losing energy. The piston will have to get bigger as we add temperature to this gas because it's movable, and so we expect some expansion and a negative sign of work. The last thing we'll talk about in this video is the idea of path independence and dependence and how these relate to work, heat, and internal energy. So delta E is what is called path independent. So if we're talking about the change in energy of system, this value of delta E doesn't matter how we got there. So in other words, when we're talking about the weightlifter, if we took that weight and our weight was the system and we had someone lift it up, or we raised it with a chain, or we raised it with a piston, it doesn't matter how we did it. The transfer of energy is going to be the same total amount because the potential energy of this object changed by the same amount, no matter how we got there. So how we did it doesn't matter for delta E. And for things that are path independent, we call them state functions. The reason we use this idea is because what matters is just where the state was at the beginning and where it ended. How it got there isn't important. So any state function is just a property of where you're at a given time, and any delta in a state function doesn't matter how you made that change, just where you were to begin with versus where you're at in the ending. So regardless of how you get from an initial state to a final state, the change in internal energy will be the same. This is not true for work and heat. So here we can use this as a graph, the progress of our transformation. Here's our total energy, and we have our two different states. And let's say in this case, we are back in in-person meetings. You're here at the bottom of the chemistry building, and you're going to come visit me in my 4th floor office. Your potential energy due to gravity will change as you come up to my office, but there's a couple of ways you can get there. Now, your total potential energy, no matter how you get to my office, is going to be the same. And for any of these state functions, we'll always take the final value minus the initial value to get our change. And so in this case, your potential energy at the end would be bigger than your potential energy at the beginning when you're on the ground floor, but your delta E is going to be the same no matter what if you start at the bottom of the chem building and end up in my office. What'll be different might be the work and heat depending on how you get there. And we can model this in two different cases. So let's say you take the elevator up to my office. You get in the elevator, you go up pretty fast, and then you just walk on over. Your potential energy isn't changing because the floor is pretty level. So this might be your path to my office if you take the elevator. Another option is to take the stairs up to my office. So you'd have to walk over to the staircase a little bit and go up step by step. Your potential energy would change a little bit slower as you raise by each step, but in the end, you'd also end up on the fourth floor of the chemistry building. So delta E is the same in this case, but you can see that the work and heat would be vastly different between these two. If you're talking about just your own system, for example, you know that taking the elevator takes less work. And this is something you could actually just feel in these two processes. So when you take through the elevator, you'd get to my office, you'd be nice and cool. Whereas if you took the steps, you'd be much hotter. So you could see that taking the steps to my office, you're maybe doing more work to get there and also releasing more heat. So maybe more work is going into you, but more heat is going out, whereas you're releasing less heat from taking the elevator. And that's because you're kind of doing less work.